Chapter 2.2, Polynomial Functions of Higher Degree. We're going to use transformations to sketch graphs of polynomial functions, use a leading coefficient test to determine the end behaviors of graphs of polynomial functions. We're going to find real zeros of polynomial functions and use them as sketching aids. And then we're going to actually just briefly talk about the intermediate value theorem. Graphs of polynomial functions. In this section, you will study graphs of polynomial functions. Polynomial functions are continuous. This means the graph of a polynomial function has no breaks, no holes, or gaps. The polynomial functions have only smooth, rounded terms, and it also cannot have a sharp turn. So we can see the examples here. You should be able to trace a polynomial function without picking up your pencil. Okay, or when you draw it, it does not have any break, right? So for example, here, this one, you can draw one part of it, but you have to lift your pencil, start all over again, and go on. So in this first one, this is a polynomial function by looking at the graph. And then for the second one, this is no, right? It's not continuous. The first one is continuous. This other example here, if you trace this first one, the smooth, rounded curves, don't have to lift your pencil. And then this last example here, there's a sharp turn here, so that is not a polynomial function. So we can say this is yes, polynomial, it's continuous, smooth. This is a no, because it has a sharp turn, okay, so like our absolute value. Polynomial functions that have the simplest graphs are monomial functions of the form f of x equals x to the nth, where n is an integer greater than 0. When n is even, the graph is similar to the graph of f of x equals x squared. So f of x equals x squared looks something like this. Then if we have x to the fourth, for example, it still has the zeros here, but it grows very fast and it's more flat near the origin. Okay, it's kind of hard to tell there, but it is more flatter here. When n is odd, the graph is similar to the graph of f of x equals x cubed. So x cubed looks like this. And then if you think about the other graph, like x to the fifth, it's very similar, but again, it gets more flat near the origin. Okay, so that is x to, let's say, the fifth power. And it tells us at the bottom, the greater the value of n, the flatter the graph near the origin. Polynomial functions of the form f of x equals x to the n are often referred to as power functions. So we're going to sketch transformations of monomial functions and, showing 3 points on each. So we have f of x equals negative x to the fifth, h of x equals x plus 1 to the fourth. So if I think about negative, a negative is a reflection, and we know that we have x to the fifth is similar to x to the third. So we can say that it looks like this. It's in the center. And if I plug in a positive 1 anyway, you would notice I would get a negative 1, right? If I plugged in negative 1, I would get a positive 1. And then you just sketch it. Let's do x plus 1 to the fourth power. So that's like our x squared. We know this is shifted to the left 1. And so this is our graph of the x plus 1 to the fourth. So go ahead and try these 4 examples here. Pause the video, and when you come back, I will have the answers for you. Here we tried this out. The first one, you would move left 5, and it's a fourth power, so it's a parabola with a more flattened base near the vertex. And then x to the fourth minus 7, that's down 7. 7 minus x to the fourth, that's actually shifted up and it's reflected. Then this one we have right 3, and it's a vertical shrink by a fourth. And one thing that I did is I just plugged in a number. So I plugged in, for example, 2 2 minus 3 is, I'm sorry, I plugged in 1, 2, 3, 4. 5, I plugged in 5 minus 3 is 2. 2 to the 4th power is 16. 16 over 4 is 4. So that's how I got 2, 4. So you just plug in a number. Okay, so I just plugged in, again, I just plugged in a 5 in here and solved for it. Okay, that's it for this video. Thanks for watching.